Hi everyone, I'm Dr. Surjit Singh. Today I'll talk about the second part of the Leetcode problem, maximum stones removed with common row or column. We are given number of stones and their positions. We can remove a stone if it shares either the same row or same column as another stone that has not been removed. We are to find the maximum number of stones that can be removed. In part 1, we had discussed the DFS solution for this problem, in which we set up a graph with stones as nodes and created edges between stones with common coordinates. For details, watch the video on part 1. In this solution, we will set up a graph similar to DFS solution. However, instead of DFS, we will identify sets of stones and use union of those sets that have adjacent stones. Consider the same problem with 6 stones. So let's assume there are 6 disjoint sets to begin with. Each stone is its own representative and size of each group is 1. We initialize component count as the number of stones. We start a double loop to inspect the pairs of stones. Stones 0 and 1 are adjacent because their x coordinates is same. So we will merge their groups, for which we will call the function perform union. We copy I and j as x and y. Rx is the representative of x, for which we call the function find representative. Both x and representative of x are 0, so it returns 0, which means that stone 0 represents itself. Similarly, Ry is 1. 0 and 1 are connected, but their representatives are different. So we will merge the smaller group into the larger group. Their sizes are equal and we move to the else part. Rep of 1 becomes 0 and size of 0 becomes 2. This means that node 0 is now the common representative of 0 and 1 and their combined size is 2. It returns true, which tells the main function that we have merged the two groups, so we decrease the component count by 1. In the next iteration, the pair is 0, 2. Their y coordinates are same, so our adjacent returns true. So 0 and 2 are adjacent and we perform union of these. Both x and y are their own representatives, so the value of Rx and Ry are also 0 and 2. Smaller group merges with the larger, so we execute the else part. 0 becomes the representative of 2 also, and its group size grows to 3. It returns true and component count is reduced to 4. 0, 3 are not adjacent, so we come to 0, 4. We will merge group 0 and 4 in the same way, which gives us this and returns true and component count reduces to 3. 0, 5 and all pairs of stone 1 are not connected and the next adjacent pair is 2, 3. Representative of 2 is not 2, it is 0, so instead of x we return representative of x, which is 0. Rx becomes 0. Note, this find can become recursive till x is its own representative. We proceed to merge 3 with 0. After merging, we get this and it returns true. So component count is 2 now. 2 and 4 are also connected, but their representatives are both 0. So perform union does not produce any change and it returns false. So there is no change in component count. At the end of loops, we are left with two components represented by 0 and 5. Size of group 0 is 5, which means that it represents a group of 5 stones. The other group represented by 5 contains only one stone, so its size is 1. All but last stone of the group can be deleted, so the number of stones that cannot be removed is equal to the number of components. So final result is 6 minus 2, which is 4. There are n squared pairs of stones. For each pair, we perform union, which takes alpha n time. So time complexity is the product of the two terms. Both rep and size take memory of the order of n. In the improved version of DFS in part 1, we had changed the design of graph. Let us recall the design once again. Both x and y coordinates can have 10,001 integral values between 0 and 10,000. So we define k as 10,001. So the graph has two k nodes. First k node numbers are for x coordinate values and the next k nodes for y coordinates. We are using magenta color to indicate that we will add k to the values for y coordinates. 2 in magenta color means its value is k plus 2. Once again, we consider the same list of stones. Adjacency of nodes is as shown. X and y coordinates of every stone are considered adjacent to each other. Check out the part 1 of this problem for more details. We will now adapt the same improvement on union of sets. But in this solution, there is no need to save the adjacency list. We will use find representative and perform union functions. Assuming that each node is a separate group and each node is its own representative and size of each group is 1 in the beginning. We create an empty set to save the coordinates of the stones. We loop over the stones and extract coordinates for each stone, add k to the y coordinates and add them to the marked set. For first stone, we save 0 and k. In the second iteration, we only add k plus 1 because 0 is already present and the set don't allow duplicity. In the end, marked has 8 entries. This covers all the coordinates of the stones without duplicate entries. This means that only 8 nodes are active. Each of these is a separate group. We initialize component count as 8. Let us recall the graph used in this method. We process each stone and add k to the y coordinates. In the first iteration, x and y values are 0 and k. We perform their union. Both x and y are their own representatives. After performing union, 0 becomes representative of k also, and the size of group represented by 0 becomes 2. As a result, number of components is reduced by 1. In the next iteration, x and y are 0 and k plus 1. Both are their own representatives. 0 becomes representative of k plus 1 also, and size of 0 becomes 3. Perform union returns true and component count is reduced to 6. For next stone, x is 1 and y is k. Representative of 1 is itself, while for k, representative is 0. Representative of 1 becomes 0 and size of group 0 becomes 4. It also returns true and component count becomes 5. For next stone, x, y values are 1 and k plus 2. Representatives of 1 and 2 are 0 and k plus 2. Union converts representative of k plus 2 to 0, size of 0 becomes 5, and component count becomes 4. For stone 2, 0, x, y are 2 and k, for which rx, ry are 2, 0. After union, representative of 2 becomes 0, whose size becomes 6, and component count becomes 3. For last stone, x, y values are 3 and k plus 3. Both are their own representative, so they form a separate group. Representative of k plus 3 becomes 3, size of 3 becomes 2, and number of components becomes 2. 8 coordinates divide themselves into two groups of sizes 6 and 2. We come out of the loop. Number of stones that can be removed is 4. This time both of the loops are linear in n, so time complexity is n times alpha n. Initializing of k nodes takes time of the order of k. Rep of size uses space of the order of k. Thank you for your time. Please stay tuned.